So I've had bad news. I've been lying to you. Matter of fact, all science has been lying to you since the middle part of this chapter. We talked about ideal gas. Okay. Now, there's an important word when I talk about ideal gas, and that word is ideal itself. It's the word I can't pronounce. Ideal. It's ideal. Okay. That means that it's idealized because it's a math function. In the real world, there's other things at play which can screw up ideality. Now, if you look at this little graph that's behind me, and this graph is on page 419 of your textbook as well, and it's a very good graph to look at because what it does is it tells you that there's a real world application of gas law, and it's not perfect. Not perfect! Ah, another perfect! And this one has to do with what happens, okay, to this value. So what I'm looking at is I'm plotting what the value of PV over RT equal to. And if I have 1 mole of gas, what it should look like. So if it's ideal, I get a little dot right here. So all ideal gases should be this, regardless of temperature, regardless of pressure, the volume, whatever I do to it, doesn't matter. Okay? But I don't see that. If I take different materials that are gases, like this orange one, that's hydrogen H2. You think it's pretty small, not a lot to it. It should behave like an ideal gas, and it doesn't. Okay? N2, okay, as I increase pressure down here, it's going to act weird, right? Same over here, methane acts weird, carbon dioxide acts weird as well. As I increase the pressure here, things are not acting like ideal gases. Now, what the heck is going on? If I look at 0, we'll look at 1, 1's way down here. Things still act pretty much like an ideal gas at 1 atmosphere. So at 1 atmosphere pressure, sure, everything acts as an ideal gas. But when we start looking at things in their high pressure, okay, things change. What is going on? Okay, there's a couple of assumptions that I had to make for an ideal gas. My first assumption that's over here is that all ideal gases takes up no volume. Right? So no ideal gases, they take up no volume at all. Right? So that means that the atom itself has no volume. Kind of a strange concept in the world of chemistry. Everything's dominated by matter and energy. You can say that the matter doesn't exist, chemistry kind of disappears. But in order to make ideal gas law work, we have to assume that the atoms of gas themselves take up no volume. Okay? And when you look at 1 atmosphere of pressure, if you look at everything that's in a large container at this point, you look at that 22.1 liters, standard conditions, 1 atmosphere of pressure, 0 degrees Celsius. You look at the conditions in there, it's very idealized. There's a lot of empty space for those molecules to run around through. So it's like they don't have any volume. But as pressure increases, okay, we're beginning to take that reality and we're beginning to squish it. And we squish that reality down and we squish it into a little section and say, you know what, as things get closer, their volume is going to start to matter, right? So here, as I increase the pressure, what I'm doing is I'm decreasing volume. So the pressure squeezes these things. Increase the pressure, okay, I'm squeezing it down. I have to because that's the relationship that's associated with things. As pressure goes up, volume has to go down in order for the number of moles to remain at 1, okay? And it's not exactly working. And the reason being is that, well, I hate to break it to you, but atoms and molecules, they do occupy some volume, okay? So that's one thing that we have to worry about. The other important thing that we have to worry about is that, so this is 1. Number 2, okay, is that collisions are not perfectly elastic. Right? So that means that when molecules run into the side of the container, they run into themselves. Sometimes they don't bounce off of each other the way that they should. They're not perfect little round superballs. Sometimes they interact. And this comes from van der Waals forces, van der Waals interactions. And when that happens, it's going to screw up our measurements. So we have to apply a couple of corrections to this to make sure that our ideal gas law actually works. So ideal gas law is nice for idealized situations. But when I get to high pressure situations or large concentrations in a specific volume, okay, those types of things I have to worry about with gases, Now I'm going to start running into something that needs to be corrected a little bit. So this is the van der Waals correction to the ideal gas law. Let me erase and I'll put it on the board. So here I've got PV. These are the things that are really going to be affected by our change in pressure and volume. Okay, number of moles we're going to keep the same. Temperature is going to try to keep the same with that as well. Okay, gas constant obviously is going to be the same. But now we have to apply corrections that account for the non-elastic situation of the molecules colliding, as, as well as the fact that they take up space themselves. Okay, so what I do is I break this down, and everything is still going to be equal to nRT over here. Okay, and what I've got for pressure is going to now be a term that's defined by this. N2 over V2, okay? N squared over V squared. And what this represents, okay, is that as the number of moles goes up versus my volume, okay, as this goes up, my idealized pressure is going to fail. So I have to account for the fact that my pressure is actually going to be higher at this point, okay, thanks to the fact that I've got a lot of moles here, or my volume is diminished, okay? The second correction that I have to do is to volume. And volume is going to be equal to minus NB. In this case, N again is number of moles. What that means is that, guess what? Atoms and molecules take up volume. So I have to account for the fact that there's moles of gas that are present. Okay, now depending upon the gas that I use, I've got two constants that I've now defined here. Okay, A and B. So A and B here, both of these are constants dependent upon the gas. And these values have been measured. Okay, so what I'm going to ask from you guys is to go look on a test, find the table, be able to put these on, and figure out how to determine idealized values for gas law equations, right? All from this particular equation and its new fix to the ideal gas law to account for those weird perturbations that we get when pressure and volume get too large. Okay.